Hey everybody, my name is Noé Barrell, and I'm kind of like the head engineer for machine learning here at Deque Systems. And I'm here to talk to you all today about how we're using machine learning to tackle accessibility. What started a few years ago as an experiment in a Jupyter Python notebook has now been integrated into several products and kind of begun to transform the way that we're thinking about accessibility testing. So I'm going to share my insights over the years and exactly how we're applying it. So first, I want to talk a little bit more generally about machine learning and where things are today. So I'm sure you've heard a lot of hype lately about machine learning and that we're in an ML revolution. Soon we'll be reaching general AI. Um, Maybe not, but over the past few years, ML capabilities have certainly advanced very rapidly. Um, I think it was in the 1980s, actually, that convolutional neural networks were invented for the first time. And then it wasn't actually until 2012 with AlexNet that they gained relevancy. And kind of at the same time, around that 2010, 2012 area, natural language processing models also started to really take off. And in the past 11 years, there have been significant advancements in NLP, computer vision, and many other fields in machine learning. And these, in my mind, are owed to several different things. Well, first of all, with more time, we've had a lot more time to collect data, and also a focus on high quality data. And that's very important. That's been one of the things that we've been focusing on a lot here at DQ. And so we have larger data sets now, better data collection methods, and also, in my mind, better data management practices. It's important as you scale up your data sets to make sure that you're not introducing any noise and you're targeting your data collection in areas that will actually see improvements for your artificial intelligence algorithms. Also, there have been more advanced algorithms. As I mentioned, the basic convolutional neural network has been around since the 1980s. So all things considered, it's a relatively basic piece of technology. But since then, significantly more advanced approaches to computer vision have come out, and those have really helped drive performance in artificial intelligence. And then finally, there's more advanced hardware to train the neural networks on. These GPUs that we have today are very good at processing large amounts of data in parallel very quickly, and they've made it very easy to train on large data sets and see huge gains. And I'm sure recently you have all heard about a couple of neural networks that have been generating a lot of hype. Both of the ones that I'm going to talk about are from OpenAI. First, over the summer, there was DALL-E 2. This is a neural network, if you're not familiar, that you can give an input sentence to that describes an image or a piece of art, and it will generate several random outputs based on that description. So you could say something like a Monet drawing of hay bales in a field, or you can get a lot crazier than that. I certainly had a lot of fun with it. But that was maybe the first thing that kind of came out over the summer. And then more recently, there's been ChatGPT. And I'm sure most of you have heard about this, but if you haven't, that's a neural network or an artificial intelligence algorithm that you can basically ask any question or give a coding task. And with limitations, it will output in very simple and easy to understand form an answer to your question or prompt. It's worth noting that this ChatGPT algorithm doesn't actually work particularly well for accessibility. And that's because it's trained on a very large general data set on all the code in the internet that it has access to, which, as I'm sure most of you know, is not particularly good for accessibility. And so it's clear that to tackle accessibility, we need a specialized model, and it needs to be trained on specialized data. And that just isn't something that existed before we, or at least existed publicly, that before we started to tackle this problem. And so I'm going to talk a little bit about where I think machine learning fits into accessibility testing. I believe that machine learning is well suited in instances where you want to understand something a little bit deeper than what's just there in the programming. You want to understand what the role is of an object or what the significance is in a user interface. And so we use machine learning to infer the role that an object in a user interface performs, and that can help us check that it's programming what we can see in the markup and the programming meets certain conditions. And this is helpful for a variety of reasons because it reduces the amount of fully manual testing It reduces the amount of knowledge required to test things, and it also increases the efficiency. Here at Deque, we address this particular problem by using several machine learning techniques, optical character recognition, and more broadly, computer vision. And a few years ago, it became our mission to achieve a large-scale, high-quality, accessibility-focused data set and algorithms designed to interpret user interface design. Just a note about machine learning. Machine learning is a statistical, mathematical approximation of real-world data. And unless you contrive a very simple, very basic example, it is impossible to get everything right. On the right here, I have plotted what's referred to as a decision boundary. And you can see that the decision boundary does a pretty good job of separating the blue and orange points into their respective classes. Everything on the one side of the decision boundary will be in one class, and everything on the other side will be in another class. But unless you come up with an arbitrarily complex decision boundary, which will actually hurt your performance on real world data outside of what it was trained on, you're going to get some things wrong. And so the algorithms and tests that we use for our the algorithms and the tests that we power with machine learning models are designed to account for this natural error tolerance that we have with machine learning models. Instead of using machine learning models as a source of truth, we use them to kind of guide users into accessible design and to finding the correct way to program their websites. So here at Deque, we use computer vision to tackle this semantic role problem. Our machine learning models actually look at a web page and they analyze the visual appearance of all the components on the page, and they also compare them to one another to incorporate more context. And we determine what the role of everything on a web page is, whether it's interactive or structural. So for instance, a structural component would be something like a heading, a navigation area, list, table, etc. And then the interactive ones could be buttons, sometimes icons, tabs, list boxes, inputs. And we have been leveraging over the last few years our large user base to help us collect machine learning data. We have a huge amount of customers and thus a huge amount of screens that we can train on. Our algorithms have been trained on data that has been collected over several years. We have at our disposal several hundreds of thousands of user interface screens to train on. And the humans that label our data, because it's very important, you can't just rely on what's in the markup and in the wild, because as we know, that is not very reliable for accessibility. So we actually have humans that we employ that are trained on user interface design patterns to verify the accuracy and integrity of our data. They make sure that what is labeled and what input into our neural networks is consistent with what is actually semantically there on the page, not what's in the markup. And so this ensures better accuracy for our machine learning models, even though it is slightly more time consuming and expensive to collect this data. So here's an example of what we use computer vision for. As you can see here, we have a screenshot of a flight checkout page. You can select, there's a list box to select whether it's a round trip, a one-way, or a multi-city. There's a date picker pop-up button, another list box to select the number of passengers, a submit icon, and then 2 checkboxes, and then another list box for an advanced search setting. And so our machine learning would look at this web page and output a bounding box around every single prediction, every single element on this page and what it thinks its role is. And then we will take that markup, or we will take that prediction from the machine learning and compare that to what's in the markup. And this allows us to test things further, and it also allows us to make sure that they were programmed with the correct role. So one of the first examples of how we use this in the real world is in our interactive elements tool. Our machine learning based interactive elements tests actually analyze web pages on their visual appearance, and it checks that the semantic role of objects on the web page match what the machine learning thinks it is. Just like a visual user would look at a page and see like, okay, here's the submit buttons and the inputs. Our machine learning is able to do that. And then we take this inference and we compare it to the markup, and this allows us to check that the role that is there makes sense. And once we believe we know what the role of something is, we can test it further. If we know that something is an input, we know that it also has to meet certain criteria. So we identify interactive objects from the following set. I'm not going to read them off, but there's about 20 interactive objects that we currently identify. Like I said, probably the biggest ones are navigation items, list boxes, inputs, radio buttons, checkboxes, and text buttons. So here's an example on the Amazon Web Services login page. At the top, we have a heading that says sign in as an IAM user, and our machine learning has identified basically everything on this page. So we have the image icon for the AWS logo. We have the image on the right for AWS Gravitron, all of the inputs. And note that we've also identified here, it's a little bit hard to see, but we've identified all of the inputs and the input labels that are associated with them. So now we can associate inputs and input labels together based on using machine learning, based on a visual basis. So we don't need to rely on what's there in the markup to know which inputs are associated with which input labels. And then going down, we have a checkbox, and we've also identified the associated text with that checkbox. Remember this account. And then a sign-in text box. And then the two links at the bottom for sign in using root user email and forgot password. So this just kind of shows the power of our machine learning. We can basically identify everything on a given web page with type bounding boxes, and also associate things with one another based on their label or their associated text. And so this can be very powerful. And then looking here, we have an example of the Walmart homepage. And again, I just want to point out that there are many, many, many different interactive and structural components on this page, and our machine learning has basically identified all of them. At the top, we have a navigation menu with several icons and navigation items. And I've omitted some of the labels here just because it would be pretty cluttered if we printed all of the labels on the page. But I've pointed out that we've identified the 3 buttons on this page, the slider on this page for the video that plays when you load it. There's a list box at the top that allows you to select how you want your items that we've identified. And then there's also this modal down here where you can reserve a time to pick up items at a store or get them delivered to your home. Also of note is that there's several nested presentational tables here or layout tables here on the page. And we've identified all of the larger presentational or layout table, as well as the smaller nested ones. And inside of each of those, we've identified the cards and the headings and the images. Also, there's an input at the top we've identified with the search icon. And so we're able to look at a web page like this with a lot of stuff going on and a complicated nested structure and identify all of the things that are happening on it with a single pass through our machine learning algorithm. And here we have the Open Snow website for my personal favorite ski mountain, Mammoth Mountain. And of note on this web page is that we have a navigation menu and a tab menu. These things are in many ways quite similar, but I believe that they have an important difference. And our machine learning algorithm is actually able to tell the difference between these things. Again, I just want to point out that our machine learning has basically identified every single interactive and structural component on this web page. But I think one of the more impressive and noteworthy things is the difference between the navigation menus and the tabs. Not only can we identify where the tabs are, but we can identify which particular tab is selected, which can be very useful. And then moving down, we've identified the button to show a map, all of the headings, all of these list items down here, and as well as the icons and the input fields of the input search field at the top, and the switch down here at the bottom. So again, we can look at another page like this and identify kind of a nuanced difference between a tab list and a navigation menu. And then here, this is showing in our interactive elements tool what we actually do with this output. So this is from the Eastern Sierra Avalanche Center. They're a great nonprofit resource that outputs forecasts for avalanche danger on any given day. I went ahead and analyzed their page on our interactive elements tool, and I found, maybe a small issue with it. So looking at this navigation menu at the top, you can see we have kind of a nav bar at the top that has forecasts, weather, observations, accidents. And the navigation item that we're looking at right now is labeled accidents. And this has been marked up as a list item. But here in the interactive elements tool, we say that the calculated role for this element is list item, but our AI detected that this is a menu item. Is our AI correct? And you could argue that list item or maybe some other markup for this this accidents thing is correct. And so that's why instead of telling the user that they are wrong, we ask a question to guide them towards the right accessibility to the right accessible markup. We give them the option to say, no, actually your AI is wrong here. Like we like the input that we have more. But I believe that in this case, menu item is probably the most correct markup. And so here again, we have another example of a flight checkout page. And in this one, there's two checkboxes at the bottom and their associated text, add a flight and add a car. And again, I just want to point out that we've identified everything on this page, the input for going to, the pop-up, the date pop-ups for check-in and check-out, and the pop-up for the number of travelers, as well as the tab list at the bottom, and in particular, which one is selected. It can tell just from the difference in color of the text that the left one, the one that says stays, is selected over the other ones. And this is because of the approach that we use with our machine learning, where we actually, instead of considering objects individually from one another, we look at them and we actually augment our object detection network with a module that considers object detections relative to one another. And this allows us to do some really neat things like selecting which one is the selected tab. Because ordinarily, if you're just looking at a tab alone, you'd say like, oh, blue's a fine color for a selected or an unselected tab, and we'd have no idea which one it was. But because of our advanced artificial intelligence computer vision algorithm, we're able to tell that the difference in color between these tabs means that the left one makes it selected. But the also of note, this is looking again through our interactive elements tool, IGT. We have these two checkboxes over on the left here highlighted and flagged for a potential accessibility issue. These have been programmed using a div class with no provided role. Our machine learning is able to look at these and know that these are a checkbox, and also the text that you click on here is interactive and will select the checkbox. So our machine learning algorithm is able to look at this and see that there's no role provided, and then ask the user a question about whether or not there should be a role provided. And it will also suggest that checkbox is the correct role in this case. And so one more example here through the interactive elements tool. Here we have kind of this tab list at the top of this web page. It says ontologies, features, metadata, and functions. Those are, in my opinion, the 4 tabs in this tab list. And the provided role of the features tab here, we're looking at the features tab, the second one, which is an unselected tab. The provided role for that one is button. And you could argue that a button is a fine role for this, this tab in this tab list. But I would argue that because only one of these things can be selected at any given time, and the focus changes based on which one you select, that our AI is actually correct in suggesting that tab should be the markup here. And so again, instead of telling the user that they're wrong, we ask them a question based on what our AI thinks is going on. And so we say the calculated role for this element is button, but our AI detected a role of tab. Are we correct? And then we give the user a chance to say, no, we're not correct, or yes, we are. And so this can help guide you towards a more accessible design more efficiently and more effectively without inserting a potential false positive for machine learning based on our machine learning detections. And so another example of a case where we use machine learning is not just with the interactive components, but also with structural components. So we actually use machine learning to look at and interpret the structure of tables. We can tell what the headings are, or what the table row and column headers are. And similar to our interactive elements tool, we check that the visual semantics of the table structure matches how they're programmed. And so we look at table cells, table headers, etc. And we make sure that what our machine learning sees and interprets on the page matches our understanding of what is programmed there. And then we can also identify other structural components as well, such as layout tables, lists, headings, input labels, and their associated input, as I already showed you. But right now in Axe Pro, we just have the table tool. So here's an example of that. Here I am looking at a comparison table for different ski bindings. In case you couldn't tell, I enjoy skiing. But this is a complicated table here. We have multiple headers on this table, both for columns and for rows. And in fact, for the column headers, we have two on top of one another. The first column header here is an image for the binding, and the second one is actually the name of the binding. And then on the left, we have headers like image, product, rating, availability, price, etc. So our machine learning will take a look at a screenshot of this table and analyze what it thinks the headings and the table cells are. So in this case, the first row, the images, have correctly been marked up as headers. And all the columns on the left have also correctly been marked up as headers. But the name of the binding, which is a header for the price and all of the weight and all the other information about the binding, has not been marked up as a header. This has been marked up as a data cell. So our machine learning is able to look at this complicated table, this very complicated table example with multiple layers to it, and determine that the second row is actually a row of headers. And so then we take a look at this one. In particular, the one that we're interested right now is the Hagen pinup Evo binding, right here in kind of the top left area of the table. And we're able to look at this and say, this has been programmed as a data cell. Our AI identified this as a header cell. If that is correct, please click the "This is not a data cell" button below. And so again, we ask the user a question and use our machine learning to guide them towards the correct markup for this table. And so now I want to take a step back and talk about some of the unique challenges with machine learning in user interface interpretation. So when we started this project several years ago, there was really almost no prior work done or research done, very limited research done on using machine learning or computer vision to interpret web pages and user interfaces. And there's a couple of unique problems with using computer vision on a web page or user interface. So for instance, user interfaces can be very densely populated with objects. You can have a lot of objects on top of one another, right next to one another. And so you need a network that can efficiently process all of these objects and consider them. And then also user interfaces have objects of very large and very small relative sizes. So consider the example of an icon, and then compare that to a footer or a navigation menu. The relative size of those is a factor of many tens, maybe even 100. And so to be able to, with a single pass through our neural network, efficiently consider objects of very different sizes is also another technical challenge. And then there's the challenge of the data. Like I said, all of the data that is out there for user interfaces or for the web is not with accessibility in mind. And it actually is going to hurt your detection capabilities if you tried to train on any of that. And so we had to collect our own data. And we also need to ensure that the data is labeled manually by humans that are trained in user interface semantics. And so labeled training data can actually be quite time consuming and expensive to collect because of how many objects can be on a page and how big pages can be. One screen can take up to 30 minutes for one of our experts to label manually. And so it's taken many years to grow our data set to the size that it is. And also it's very important to ensure that as our data set grows, we do not sacrifice quality, because it's very easy to just add a bunch of low quality data and then just train on it and hope for the best, but your algorithms are going to suffer if you do that. And so we really need to ensure that as our data set grows, we don't sacrifice the quality of our data. And then we need to ensure also that the labeled data points of our data set actually add to the diversity of our data. And we're not just collecting a bunch of data points that are like what we've already seen or like what we're good at. And so we have implemented some targeted data collection methods to ensure that the data that we do capture is improving our models so that our investment in this area is kind of targeted. Also, I want to talk a little bit about how our algorithm specifically works. I mentioned that it considers objects relative to one another. So we do this by actually including a module in our object detection network that considers object detections relative to one another. So in that tab example, in all of the tab examples, actually, it would be impossible to tell whether or not one tab is selected or not by considering it on its own. But because of this module in our neural network, we can consider the relationships that objects may have with one another. And there's a lot more complicated and maybe nuanced examples that you could think of in a user interface, like, okay, you've always got a search it icon next to the input in the navigation menu, or something else. Maybe even nuanced relationships that we can't even understand, that our neural network is able to encode implicitly about the relationships of these objects to one another. And so this has helped us significantly in our detection capabilities. Like I said, the selected tab example is probably the easiest to understand, but there's a lot of other places where before, when we weren't using this approach, we just weren't seeing the best detections. And then once we implemented this approach, we were all of a sudden seeing much more consistent and reasonable detections coming out of our neural network. And so this has been a project several years in the making. When we began, I mentioned that this kind of started as an experiment out of a Jupyter Python notebook. And we were just seeing what was possible with artificial intelligence and accessibility, because really there was nothing that existed at this time. And even in the broader field of user interface interpretation with machine learning, there was, again, not really much out there. I remember trying to find a bunch of papers and looking through the internet to see what people had done, and it was really quite limited. So we were forging a path on our own, and kind of it was very experimental at first. But over the years, our data sets have grown considerably, and our algorithms have advanced to the point where now machine learning is kind of shaking up the way that we think about accessibility testing. And also our data management practices and targeted collection efforts have helped our advancements significantly. So over the years, we've gone from just a very experimental, basic approach to very complicated approaches that actually help and see real results in accessibility testing. Machine learning is real, and it's here, and it's going to change the way that we think about accessibility testing, and we've been working on it for years here at Deque. So I believe there's a couple things that set us apart here at Deque with our machine learning capabilities. Well, first of all, we have a lot of customers, which helps to inform our machine learning algorithms, because our customers allow us to use their data to train our machine learning algorithms. Also, we have a complicated and continuous automated data pipeline. So every time we see a data point, it gets integrated into our data pipeline, and it allows us to learn. So if we get something wrong in our interactive elements or our tables tool, our users will let us know. And we actually use this as a future training example for our algorithms. And so the amount of time between when we see something and we get it wrong and when we learn and that we have a deployed model out in production is at most 2 weeks. And our computer vision algorithms are designed specifically to meet the concerns of user interface design. As I mentioned, there was very little out there before we started this, and we are using this relationship module in our neural network to specifically target the user interface design specifics and the relationships that objects have to one another. We also have a team of expert human labelers that are trained in user interface semantics, and they verify the accuracy and integrity of every single data point that we have. And we also use some unsupervised machine learning methods and human input to perform targeted data collection to ensure that any investment we have in our data set does not go to waste, and that all the data points that we collect are actually helping to improve our networks. So we have access here at Deque to possibly the largest accessibility machine learning data set in the world. We have at our disposal several hundreds of thousands of user interface screens, and we train on all of those that have been labeled and verified for their integrity. And each user interface screenshot has all of its components labeled structural and interactive by these experts. But that's, like I mentioned, that can be very expensive and time consuming. So we do a couple of things here to increase our labeling efficiency. First of all, our machine learning models are used to pre-annotate each data point. so that our labelers aren't just starting from scratch, they're actually correcting the template label that we give them from our machine learning model. And we found that this improves efficiency from anywhere between about 25 and 50% during the labeling process. And then we also use unsupervised machine learning model methods to compare our potential data points to one another. So if we know that we're doing poorly on one class and one object in the user interface, we can actually use some of these methods to automatically suggest future data points as training examples. And this helps us to really speed up and target our data collection and make sure that our investment is well spent. And this has significantly improved the gains from our models with less time and financial investment. And so we're able to more quickly deploy models that have improvements and more quickly see gains and improvements in our machine learning models. And so I mentioned we have a continuous and automatic artificial intelligence data pipeline. So I'm just going to give you a walkthrough what this process kind of looks like. So our user will use an Axe DevTools application, which captures a screenshot of their user interface as well as other data. This data is then sent to automatically through one of our deduplication methods, so that we're not getting a bunch of duplicate data in our process. And then we use some of our unsupervised machine learning methods to select and suggest some of this data for labeling. And then we use a platform called Labelbox. They're a great platform. I've been working with them for several years, actually since college. And I gave a talk about data management practices at a conference late last year that was hosted by Labelbox. But yeah, we import all of our data to Labelbox, and then these data batches are reviewed and pre-annotated by our computer vision model to speed up the labeling efficiency. Also, we have some additional data streams that we capture user interface data from, and we import those to Labelbox and perform the same process on them using model-assisted labeling. And then this is one of the human steps in our data pipeline. Humans will actually correct these model-produced labels and verify their integrity so our model doesn't lapse in its performance. And then these labels are used to train our computer vision model. And then we will assess the results and the accuracy of our new model to make sure that it looks good and it's improving. And if it needs refinement, we can update the labels, collect more data, or maybe fix some of the data, and then retrain the model. But if it looks good, then we will deploy our model to our AWS services for use by our IGTs and other DQ teams. And this happens on a bi-weekly cadence. So as I mentioned, the time from when we see a data point, get the answer wrong on it, and learn about that data point and deploy the correct model that has seen that data point is at most 2 weeks. And so every time a web page is analyzed, just to summarize, every time a web page is analyzed, a screenshot is captured. It's important to note that if for security concerns or other reasons, you don't want screenshots captured and in our data set, you can opt out of this. And this screenshot is then analyzed by our computer vision models for user interface semantics. The model's predictions are then checked for correctness by our human labelers. It's very important to make sure that we do that. And then a new model is automatically updated and tested on a bi-weekly basis. These models can be deployed according to their performance and the time from when we see a user interface prediction and get it wrong to when a new model is trained on this adversarial input is at most 2 weeks. So to summarize, we are using machine learning to simplify several parts of accessibility testing. And this means that we can reduce the barrier of entry to accessibility testing. We can increase the efficiency by reducing the amount of manual testing required. And we can allow for further testing of components before they need to be fixed to match their appearance. So if we know what a component is, it doesn't need to be fixed to test. If we know that a component is an input, it doesn't need to be fixed to test input related things on that component. Our machine learning knows that it's an input, and we can do those input related tests. And this can also be very useful during the design process. We can suggest fixes during design. So if you've been attending other talks, you may have heard of Axe for Designers. But I would like to reintroduce or introduce that to you now. This is a free open beta available now. It was released, I believe, on March 15th, so yesterday. And this is a Figma plugin for accessibility that helps designers create accessible user interfaces during the design process. we find that about 2/3 of user interface issues or accessibility issues start during the design process. And this is actually powered by our machine learning. So one of the features that is available now is machine learning automated annotations for components. And you can select from a set of components which classes you would like our machine learning to automatically annotate. And this provides a short code recommendation to make sure the intent is correctly programmed. And it has access to our extensive library of accessibility annotation categories that I shared with you earlier. And it is powered by our computer vision model designed specifically for accessibility. And soon we'll be suggesting alt texts for images as well as other components. But for right now, we just tackle the form fields, like the inputs and the text buttons and whatnot. And this is available for your use and experimentation now. So as you can see here, we have a screenshot of the plugin on the right. And you can select what kinds of annotations you're looking for and whether or not you want our machine learning to help you auto annotate during the design process. And you can select from a large set of objects, but right now, the ones that you'll see available for machine learning powered auto annotation are just the form tools, the form fields. And so here's another example. In this, we have just a basic login screen with an email, a password, and a login button. And our machine learning is able to look at this and suggest during the design process that the input type should be text for both of these inputs, and the input type for the login field is a button. And this is very huge because if you can ensure that the intent of your design is correctly conveyed to the developer, you can eliminate, according to our research and insight, up to 2/3 of accessibility issues. And so just a little bit more about X for Designers. All of these annotations from our machine learning will be inserted on top of the selected design without disturbing the design or changing it at all. It will just give you the option to use it should you find that the machine learning is correct. And then you can remove or modify them if the machine learning is not correct. And it's available now. So you should all go and try it out. And like I said, soon this will be expanded to all interactive and structural components, but for right now, we're just doing the form fields. And then soon we'll be using machine learning for a variety of other ways to test the alt attributes of images and icons. But for right now, X for Designers just uses machine learning for the forms. And with that, I think it's time for some questions if we have any.
Great job, Noé. Attendees loved your content, and we have tons of questions. So I'm going to jump right into the first question here. All right. One of my most reappearing challenges is detecting div buttons, such as missing role, no ARIA label, mouse-only functionality, as at least most have a class like BTN, button, primary, etc. There's two questions based on this challenge. Can't AI also identify these?
So to that, I would say that yes, absolutely, our artificial intelligence is capable of identifying those things. Awesome. If it looks like a button and functions like a button, our AI will almost certainly be able to identify that it is one.
Okay. The second part of, or the second question, for enterprise environments, can the AI be trained locally to handle special cases within a highly confidential government environment in Europe?
Yes, this is also possible. Okay. And that there are a couple of technical considerations with this, but it is certainly possible to deploy our AI locally in a secure environment.
Great. Next question. How do you handle ultra-flat design where interactive elements look like nothing at all, or elements that don't have a universally agreed upon UX, like hamburgers, which are sometimes buttons, sometimes links, and sometimes drop-down expanders?
I see. So for the flat design, I think it would depend very much on how flat or different it is from what we've seen before. But I would think that in most cases, our machine learning could do a pretty good best guess as to what's on the page. And that's why, again, we use the machine learning not to tell the user that they've programmed their website correctly, but to try to guide them towards the correct answer, because it's possible that we'll get something wrong. But I think generally for a flat design, we'd get it for the most part right still, because we have a lot of very diverse data in our training set. And then for the hamburger icons, I think we'd probably be able, so our machine learning, we actually have machine learning that is able to look at icons and figure out exactly what kind of an icon they are. But I would say that we'd probably leave that again to guide the user to the correct answer or to what they are intending, rather than telling them universally that there is one correct way to do things. We would ask them questions that help them figure out what they want to program.
Okay. Next question. Could AI be used to fix accessibility issues?
Yes, certainly. And that's something that we're experimenting with now. But I think rather than fixing them and potentially introducing an incorrect fix, it's better to help guide the user and make sure that our AI is doing what's intended. So I think that the way that we're using it to kind of ask the user and guide them to the correct fix is probably the best approach for now, because as I mentioned, machine learning models are statistical. They do get things wrong. And so it's best if there is still some level of human intervention before we let the AI take over completely and potentially make some incorrect fixes. But that's kind of what the Axe for Designers is also targeted to do. We can use our machine learning during the design process and suggest fixes before it even gets out there. So yeah, and during this is a Figma plugin too. So I think that this is probably the best suited application of our AI capabilities to fixing accessibility issues, because it will actually fix them during the design process if you're using this plugin.
Great. And you answered a few other questions with that answer, so that's great. Okay, next question. I think this is related to when you were talking about intelligent guided tests. For those cases where you ask the user, it seems to assume that users know that they're doing and can make a good decision. Do you review their answers? Do their answers influence your model? I assume you're opinionated and have a view on what the correct answer is.
Right. Yeah. So we do actually review their answers, and their answers do influence our model. So when we know that we get an answer wrong, we are much more likely to consider that as a future training point than something we got correct, because it's the examples we got wrong that are much more valuable towards driving a machine learning model improvement than the answers we got right. If we're getting it right, it's not really going to help us out that much to train on it. Obviously, sometimes the user may be a little bit stubborn and may tell us our machine learning is wrong. So we do review that. We don't just take their answer as a fundamental source of truth. And also it matters that we have consistency in the way that our data is labeled. So if we've always labeled something in one way in our machine learning model, even if that, maybe it's a little interpretable, it's important that we continue with that consistently, so we don't confuse our machine learning model during the training process.
Okay. Next question here, and thank you everyone for such great questions. Please continue to upvote so that we can get to as many as possible here. Is there a reason why you only refer to the visual of a page and not the HTML? Do you manage to get more of the context doing it that way?
Right. So the way that the HTML of a page is not exactly reliable from an accessibility standpoint. And it doesn't always tell us what the role is. And in the cases that it does tell us what the role is, we don't actually need machine learning to help us with that, because we already know it's already there. And so that's why we look at it on a visual basis, because the visual appearance and how a visual user might interact with a page is probably obvious to most people. But if it's not there in the markup, then there's a discrepancy, and it's going to be confusing. And so that's why we look at the visual of the page and not the markup, because the markup can be incorrect. And that's also why we help use this artificial intelligence again to guide the user in the correct direction. We say, hey, it looks like this thing that you have here on the page should be functioning as a button, And we just want to make sure that that's consistent with your intention.
Great. Okay, question here on false positives. There is a lot of checking for false positives, which is good. Do you have any data on the current false negative rate for your model?
Right. So we do have data about the false negative rate. It varies somewhat widely based on classes. I would say that we hardly ever miss things like text buttons, inputs, icons, navigation menus, and navigation items. But then there are some cases that are a little bit more complicated that we might miss. And there's always going to be edge cases here and things that we haven't seen before. So I'd say for the most part, we are missing less than 1% of text buttons, for example. But the data does vary widely on classes, and we are better at some things than we are at others, and there are always going to be edge cases.
Okay, great. Do you test on different viewport sizes and different device types?
Yeah, so currently we just test this computer vision that I demonstrated today is only in effect for the web, so for HTML. And we do test on a large variety of different viewport sizes. Our machine learning should be equipped to handle screens that are very long and screens that are kind of flatter and shorter. So we've incorporated a large variety of different aspect ratios and image sizes and web page sizes in our training set. And we should be able to handle just about anything that we see.
Great. I think we have time for a couple more questions here. Can AI be used to detect lost focus issues, such as not returning to a trigger button after a dialogue is closed, etc.?
So to the best of my knowledge, we are not currently using this technology in that way, but certainly I would see that as a possibility and something we'll explore in the future.
Okay. How do you handle if there are visual indicator issues, like if a checkbox looks like a radio?
I see. So if a checkbox looks like a radio, our machine learning will probably identify that it looks like a radio and again, ask the user a question to guide them towards the correct markup or design. So we'll probably be able to identify the difference between a checkbox and a radio in most cases, and then ask the user a question based on what we're seeing and what we're seeing in the markup.
Okay. Let's see. What about using this tool to test systems that are not publicly available? How do you deal with any legal and security elements of having screenshots of different systems?
Right. So as I said, if you're not comfortable with having your user interface screenshotted, you can opt out of it. Or there's also the option to, as I think another question asked this a little bit earlier, there is also the option to deploy this locally in an enterprise setting. So there's a couple different options there, but you can also always just opt out of it completely.
All right. Let's go with one more question here, squeeze one more in. It's quite possible to create conformance semantic markup that, as an example, fails miserably in a screen reader. And then they said that the ski bindings page example would probably be bad. Could this model at some point predict that?
So if I'm understanding the question correctly, they're asking if the markup would be conformant and semantic, but not consistent with its visual appearance. Is that correct? Do you think I'm understanding that correctly?
Yes, I think so.
Yeah, I think that our artificial intelligence is already in a place where it would be able to predict that failure in a screen reader. And this is actually one of the things that it was designed to tackle in the first place.
Awesome. And with that, I do think that we are at time. Thank you so much, Noé, for a great session. And thank you everyone for attending and asking all of these great questions. I hope you all enjoy the rest of AxCon.
Awesome. Thank you all so much.
Thank you.
Bye.